everyone, welcome back to the channel. Continuing in the binary search series, this is I'm back with the yet another problem on the binary search, that is maximum median. So this problem has been taken from the Codeforces Div 2 round. So after you watch this video, make sure to submit this problem over that platform. I've attached the link of this problem in the description below. So let's read the problem statement. So in this problem, we're given an array A of n integers where the size of the array is odd, that is n is odd. We can make the following operation with this array, that is choose one of the elements of the array, for example let's say ai, and increase it by 1, that is replace ai with ai plus 1. Now we want to make the median of the array the largest possible using at most k operations. So I can perform at most k such operations, that is take out any element, increase it by 1 and put it back there. And I want to make the median of the array largest possible. So what is median? We know that the median of an odd sized sequence or array is basically the middle element after that sequence or array is sorted in non-decreasing order. That means take that sequence, sort it in non-decreasing order, or let's say 1. So after I sort it in non-decreasing order, it would be 1, 2, 3, 5, 5. Okay, now the size is 5 and the middle element is this, that is 3. So this is basically the median after I sort this array, and the median for this sequence would be 3. Now in the input will be given two integers, that is the size of the given array and the number of operations that I can perform. These are the two integers that I am given, and in the second line I am given an array of n integers for which I want to find the median, for which I want to maximize the median, and I want to perform at max k operations. And in the output I have to print out a single integer which represents the maximum possible median after k operations. Okay, so let's better understand the problem statement using an example. Okay, so here we have an example. We have 7 elements in the array and we can perform at max 7 operations. So let's sort this array. So if after I sort this array, the array would be 1, 2, 3, 4, 4, 4, 4. Okay, and the middle element is this, that is 4, and this is the median at this point. I can perform 7 operations. The operation is basically take out any element of the array, so pick any element and increase it by 1. So if I pick 4, increase it by 1, it becomes 5 and I put it back, and I can perform 7 such operations at max in such a way that this medium is maximized. Okay, so for this example, one of the ways to do so is basically okay, so I can basically increment these 4 elements one by one. So increment 4 to 5, this 4 to 5, this 4 to 5, and this 4 to 5, hence performing 4 operations. So I have 3 more operations to perform and the rest of the array is same. So if I look at this array, I basically performed this operation on first element, fourth element, sixth element, and seventh element. Okay, now I have 3 more operations to perform. So how can I perform these 3 operations? On which integers I should perform them? So for this test case, I will perform these operations over the last 3 integers and make them 6, 6, 6. 1, 2, 3. Now the median is 5. So the answer for this test case is 5. And I have performed all of the operations. Fine. even if I hadn't performed these last three operations, just perform four operations right here, increment these four integers by 1. Even in that case, I would have this 5 as median. I don't have to increment these three integers because these are not affecting my overall median or final median. Fine. So this is just an upper limit. I can perform at max k operations. If I can get my right answer in four operations, then I don't care about the rest of the operations. Okay. Now let's see how we can solve this problem. Okay, so since this is a binary search problem, we know that we have to observe the monotonicity. The pattern is same, maximize median such that sum constraints. In this case, such maximize median such that we can perform k such operations over the array. Okay, so that's the thing. Let's see how this answer, let's say x is the answer, or let's call it m. Let's call the answer is m. Let's try to observe the monotonicity in this median. So m represents the median. Now let's sort this array. Obviously we have to sort the array if I want to look for the median. After sorting, the array becomes 1 2 3 4 4 4 4, and we have 7 operations to perform. Now the median is 4. This is middle element. Okay, now while standing on this integer, that is current median, I'm sure that all the integers which are lying after this integer, that is these ones, are either greater or equal to this median or this middle element. I'm sure about it after I have sorted this array. Fine. Now that means if I increment this median by 1, then I have to make sure that the rest of the integers which are lying after this middle element stays greater than the current median. That's what I have to make sure. I hope you're getting. Let's say I increment this by 1. Let's say I assume that the median is 5. So if the median has to be 5, then I have to increment these numbers by 1 as well. I have to increment this to 5, I have to increment this to 5, I have to increment this to 5. Only in that case my answer will hold true, or my claim will hold true. That means I need to have at least 4 operations for my median to be 5. You got it? Now let's say m is the answer. M is the answer for this test case, or for any test case. Let's say m is the answer. Now what does that mean? That means if m is the maximum median which I can obtain in this array after performing at most k operations, that means I can always achieve m minus 1 as median after performing k operations. That's obvious. That means here if I can achieve 5, that means I can achieve 4 as well. If I can achieve 6, then I can achieve 5 as well. Let's say the number of operations which we are allowed to perform are 8. In that case, I will increment these last 4 integers twice, hence giving the array as 1 2 3 5 6 6 6 6. Now the median is 6. I consumed all the operations. I consumed these 8 operations, performed 2 operations over each integer. Okay, here in these last 4 integers of the array. That means if I can get 6 as my median, I can always get 5 as my median. How? Just perform 4 operations over these last 4 integers. One on this, one on this, one on this, one on this. Hence making it 1 2 3 5 5 5 5, and the median would be 5 in that case. That means I can always achieve 4 That means I can always achieve 4, perform no operation, just 4, that is the median. Now can I achieve 3? No, I can't, because even if I perform 0 operations, the median is 4. So this is the lower limit, while the higher limit is 6. I can't go beyond 6. That means if someone says me, can I get median 7 after I can perform 8 operations over this array? The answer would be no, we can't. We can't get 7. Or while on the other hand, I can't get anything less than 4. While on this side, I can't get anything greater than 6. So this is the valid range. And that means, let's say this is the last integer or maximum median which I can achieve. Like I achieved 6 in this case. So this is m. That means I can achieve m minus 1. That means I can also achieve m minus 2. Why? I can get it till the median, let's say small m. So this small m is basically the median of the given array without performing any operation. While on this side, m plus 1 is something I can't achieve, m plus 2 is something which I can't achieve, and so on. So these are the good ones. Good medians, let's call them good medians. These are the bad medians, let's call them bad medians, because we can't achieve them. So what is our target? Our target is this integer, this last good median. Okay, now I hope you're getting to which this problem resembles. In the very first video we discussed two concepts, that is first true and last true. So this is basically the application of that last true function, in which we are given this search space. We want to find the last true in this search space, namely the largest integer where the conditions are satisfied, or the last value where the constraints are satisfied. The constraints are perform at max k operations and check if we can achieve that median or not. Got it? That's all. So the lower limit for the binary search would be m. So this m is basically median for the array when we do not perform any operation. So to get this value, just sort the given array and find the n by 2th element, this element, in the sorted array before you perform any operation over it. That's this m. So this is m, small m basically. While the higher limit is, that is high. Now take this high, so take this high a very large number, or like an upper bound. Think of the case when we have extreme inputs. That means when we have largest k, that means largest number of operations, and minimum number of elements. So the minimum number of elements that we can have is 1. The maximum number of operations that we can go up to, these are given in the problem statement. Here we can see the k goes up to 10 raised to the power 9. Fine. That means this go up to 10 raised to the power 9. So, and the maximum integer that I can have in the array also goes up to 10 raised to the power 9. So this is basically a typical element in the array. This is the maximum limit for that. Now we have one element in an array, so this is the array we are assuming, and here I can perform these many operations. So when I perform these many operations, it will give me 2 into 10 raised to the power 9, which is the extreme case. Fine. We are performing all the operations over the single element of the array. Now take any test case, the median will never cross this number. So the high is basically 2 into 10 raised to the power 9. That's my search space. Okay, so I have got my search space, and now the rest is basically that is valid or the boolean function which will validate if a particular median is achievable or not. How can I check that? So let's say we have this search space. Let's guess some number m. Let's guess some number x. So we guessed x. This is the middle element over this search space. Now I want to check if x can be the median or not. How can I check it? So before I perform this binary search, I basically sort this array beforehand. Okay, so this is the input array, but I sort this array when I start my program. At the very start of the program, I sort this array. So I always have a sorted array. So the array that I have at this point would be 1, 2, 3, 4, 4, 4, 4. Now I've guessed x, that if x is achievable or not. Okay, now go to the middle element. The middle element is 4. Okay, now convert it to x, and the number of operations which I need to perform to get 4 to x would be x minus 4. This has to be positive or 0. This has to be non-negative basically, because for x which are less than the median which I already have. Okay, okay, so this is basically x minus 4. These are the number of operations which I require for my median to get to x. But these are not the only operations. I have to make sure that the rest of the elements towards the right of median are either greater than or equal to x. So for that, I also have to add x minus 4 for this element plus x minus 4 for this element, and finally x minus 4 for this last element. That means I have to make these elements at least equal to x. That means these are the total operations which I have to perform. Now here I have to check if these operations which are required are greater than or equal to, or they are less than or equal to k. Is it feasible to perform these many operations? Do we have the capacity? We ask ourselves. If we can, then we return true, otherwise we return false from the function. Fine. And in this way the predicate function works. Just get to the middle element and start traversing from that element, start traversing from the middle element till the last element, and keep on adding x minus a of I. Keep on adding this factor to a variable. Keep on accumulating this. Okay. Now at the end, check if the accumulated sum is less than or equal to k. If it is less than or equal to k, then return true, otherwise return false. That's the idea. And we just have to get the last middle. That means if x is valid, that means I can get this x as a median after performing at max k operations, then this can be the potential answer. But don't stop looking for a better answer. Let's say x lies somewhere here. Now the search space will be reduced to this one. That because we want to check for the last median, the largest median over the given search space. So now search for the possible median on the right side of this x. Or if it is invalid, if the sum basically is greater than k, that means I can't have this as a valid median. In that case, search in the left search space over here. Fine, so I hope you got the idea. It is very similar to the problems which we have solved in the previous videos. So if you have followed all the videos, you will be able to solve this problem very easily. Okay, so before you move on to my implementation, just stop here and try to implement the solution by yourself. Okay, so let's jump to my implementation. Okay, so this is my implementation of this maximum median function, which takes in this nums array, the number of elements which it has, and the number of operations which I can perform over that array. Initialize the boundaries or the search space. The least we can go is 1. The maximum we can go is 2 into 10 raised to the power 9. Now perform the usual binary search over the answer, and here check for the middle element. So here we calculate the middle. Check if the middle is valid. Check if I can achieve this mid as a valid median. If I can achieve it, then that means check for a better answer in this search space from mid to high, while this mid can be my potential answer. Okay, because I want to find the last median or the maximum median. While if it is not the case, if this mid is not the valid median, in that case reduce the search space to this one, that is from low to mid minus 1, because I will find my valid median in this search space. So at the end, after we end up performing this binary search, we have our last true stored in this low variable. So if you're not getting this definition of last true, then go watch the very first video of this series in which I explained the first true and last true functions. So this low basically will store the last integer which we want to get. So I return this answer from the end of this function. Let's see the definition of this check function, this predicate function. Okay, so this is that check function which takes in that middle element which I calculated there, the number of elements in this nums array, and the number of maximum operations which I can perform. And here this is an integer which represents the maximum number of operations which I can perform. Iterate over the array from the middle element till the last element and count the number of operations, accumulate the number of operations in this variable. Okay, so if this is positive, x is basically the median which I want to get, which I want to reach, where num size is basically the current element, and these are the number of operations which I have to put in to bring this nums I to x, and x minus nums I would be the number of operations, and I add it to the operations variable. Now this is basically a little optimization where I'm simply checking if at any particular element while iterating over this array, if the operations exceeds the number of operations which we are allowed to perform. If they exceed that, then I return false right from here, because there is no use to traverse over the rest of elements. The operations have already exceeded k. If I pass this loop, then here I have to check if the number of operations which I have accumulated over the array are less than equals to k. If they are, then I return true. If they are not, then I return false, because I can't get all the elements after the middle element, including the middle element, equal to x. So that's how this check function is working. Very simple. Let's discuss the time and space complexity. Okay, so the time complexity for the given implementation is n log n. Why? Because binary search, basically performing the binary search, takes log n time complexity, where this capital N is not same as this small n. This capital N basically represents the search space, that is high minus low, high minus low. That is this capital N. While this predicate function contributes a big of n time complexity. This is small n because we are iterating over the array here. Hence the overall time complexity becomes n multiplied by log of n. So here this there's a little mistake. This is not capital log n. This is not n capital N log n. This is small n log n. So the time complexity is n log capital N. So this is the search space, while this is the number of elements. While the space complexity is constant because I'm not using any auxiliary data structure to store anything. Fine, so that's the time and space complexity. Let's jump to the code implementation. Okay, so this is the solution class. Let's write our maximum median function. So which takes in the size of the array, the number of operations, and the array itself. Now initialize two pointers, low with 1, high with 2 into 10 raised to the power 9. Now iterate over the okay, perform the binary search. Low is less than equals to high. Calculate the middle element, that would be low plus high minus low divided by 2. Check if this middle is valid. So check if this mid is valid. If I can get this median by performing k operations over an array of size n and the array is nums. If this is true, then reduce the search space to the right half. Else reduce the search space to left half. Finally return low right at the end of this function because this is going to store my answer. Let's define that predicate function. Which is a boolean function called check. It takes in the assumed median, it takes in the number of operations, it takes in the size of the array and the array itself. Okay, so let's calculate. So let's initialize an variable representing the number of operations which I require. Iterate over the array starting from the middle element till the last element and accumulate the operations which I require. So for that I have to check if the given median which I have assumed and the current element gives me a positive value. That means if there is a scope of performing operations. If it is the case, then perform those operations. How many? X minus nums I. So at any point check if the operations exceeds k. If it is the case, then return false right from there because there is no use to perform operations because we are not left with the operations. Otherwise check if these operations are less than or equal to k. If they are, then it will return true, otherwise will return false. Okay, so this is the implementation of this solution in C++ language. Let's see the implementation in other languages. Okay, so this is the implementation in Java and this is the implementation in a Python language. Okay, so that's all for this video. If you like the video, then hit the like button and continue with me in this series. We'll be solving harder problems as well in the upcoming videos. So stay with me. I will see you soon in my next videos.